All right, welcome back to your first lecture of week 11, our second week on online instruction. First, just a little rundown of active due dates. Today, the daily homework from assigned on week 10, day 2 is due to me. Send those to me via email. Test 2 is also due today on Moodle, and your attempts will automatically submit at 1 p.m. Eastern today. This Friday, periodic homework number 5 is due. Submit that via email to me. Please make sure the problems are clearly numbered and in order so that I can find them easily. Also due Friday is the daily homework that's being assigned today, which is only one problem, and that will also be submitted by email. In case you haven't checked the syllabus schedule recently, also a reminder about something due next Tuesday. The first draft of your project is due next Tuesday to me via email. And this is just a rough draft. You don't have to have the entire thing all typed out. You don't have to have your citations in the appropriate format. But at minimum, you do need to have an outline of your entire paper, which includes a description of which novel problem that you're doing. If your paper is not headed in a direction that will allow you to tick the research box that this class satisfies, then I need to find that out early so I can give you as much time as possible to go in a more helpful direction. And since one of your periodic homeworks is due this week, it's time to assign the next one. Periodic homework 6 will cover chapter 12 and consists of these 6 problems. Now, the problems are starting to get longer, so the list of problems will get shorter, but none of these are extra credit problems. You do have to do all 6 of these problems. So that's the rundown of all the active assignments, and now it's time to get to our topic for today, which is the method of Frobenius. And the method of Frobenius is another way of finding a series solution to a differential equation when the series doesn't have to be a power series. As an example of a series that doesn't have to be a power series, we could have negative powers, like 1 over x squared times some constant. Or we could have fractional powers, like square root of x with their coefficient. And these are things that we could not have with a traditional power series. This means the form of our solution will be a little bit different, and our general solution will look like this. Y equals x to the s power times the sum from n equals 0 to infinity of a sub n times x to the n. So this is very much like our original power series, except for this factor of x to the s that we are putting out front. And there's a more helpful way to write this solution right here. Combining the two powers of x into 1, we get that y can be written as the sum from n equals 0 to infinity of a sub n times x to the n plus s. And this form of solution is called a generalized power series. A couple of things to note real quick before we jump into an example as a way to explain the process of the method of Frobenius is to note that our first term is a naught times x to the s. And that term goes with n equals 0. Since this is our first term, we are just going to assume that a naught is not equal to 0. And as far as this new constant s, we don't know what s is going to be offhand, but we will determine the value for s over the course of our solution. Just a brief note, s can be anything, real, complex, imaginary, but we're going to stick to situations where s is a real number, and for a lot of what we're doing, it will be an integer or a rational fraction. So, with all of this in mind, we are now ready to actually do an example. And the example we are going to do is the following differential equation. X squared times y double prime plus 4x times y prime plus quantity x squared plus 2 times y equals 0. And this is the differential equation that we're going to solve by the method of Frobenius. So Our first step here is just to assume a generalized power series solution, which means that y will have the following form. As we wrote on the previous slide, sum from n equals 0 to infinity of a sub n times x to the n plus s power, or written out in terms of individual terms, a naught times x to the s plus a1 times x to the s plus 1 plus a2 times x to the s plus 2, and so on and so on. The next step in our method of Frobenius solution is to write a series for each term in our differential equation, much like we did with regular series solutions to differential equations. So we currently have y, so we may as well get down y prime and y double prime. Y prime will be the sum from n equals 0 to infinity of n plus s times a sub n x to the n plus s minus 1, which we could then write out term by term as s times a naught times x to the s minus 1 power plus quantity s plus 1 times a1 times x to the s plus quantity s plus 2 times a2 times x to the s plus 1 power, and so on and so on. Note that our first term here does not vanish, unlike our power series approach, because we have no guarantee that we're going to have integer powers here, or even positive powers to begin with. So when we take the derivative of our first term, which used to be just a constant, a naught, it no longer disappears. So our sum still starts at n equals 0, even for higher derivative terms. So next, let's write out the term for y double prime, and we get the following. The sum from n equals 0, again, to infinity times n plus s times n plus s minus 1 times x to the power of n plus s minus 2. And we can write this out term by term as well. S times s minus 1 times a naught times x to the s minus 2 power plus s plus 1 times s times a sub 1 times x to the s minus 1 power plus s plus 2 times s plus 1 times a2 times x to the s power, and so on and so on. So now we're about ready to actually write out our individual terms that we're going to need later on, and I'm going to write these up in the corner here. So, using some color coding here, one of the first terms we're going to need from our differential equation is x squared times y double prime, which we can just write in summation notation by taking our term for y double prime and multiplying it by x squared. That is, we'll increase the power of x by 2, and we end up with the sum from n equals 0 to infinity of n plus s times n plus s minus 1 times a sub n times x to the n plus s. Then, for our next term, we have 4xy prime. And this, again, we can start with our definition for y prime and just multiply it by 4x. So we pick up a constant 4 out front, and we increase our power of x by 1, giving us the sum from n equals 0 to infinity of 4 times n plus s times a sub n times x to the n plus s. Then our next term is x squared times y. And we take our expression for y and just add 2 to our power of x here. So we get sum from n equals 0 to infinity of a sub n x to the n plus s plus 2. And last but not least, we have just 2y, which is accomplished by just multiplying 2 by our series for y. So that's the sum from n equals 0 to infinity of 2 a sub n x to the n plus s power. So these are the 4 terms that we're going to need, and I'm going to keep them over here in the corner and erase everything else so we can have enough room for the next step. There we are. Everything is erased now, so we're ready for step 3. And step 3 in our method of Frobenius solution is to fill out a table with the coefficients for each of our powers of x, starting our table at the lowest power of x that we have present. So we should double check each of our series here to try to figure out what the lowest power of x we have is, so we can know where to start this table. And if you just plug in n equals 0 to each of the expressions and look at the power x is raised to, we can see that for our x squared y double prime term, our lowest power of x will be x to the s. Same thing for this one in orange, and same thing for this one in purple. And for the one in green, our lowest power will actually be x squared. So this means as we start to fill out our table, the lowest power of x we're going to have to worry about is x to the s for this problem. So let's make our table. So as before, we will have columns for each of our powers of x, starting with the lowest power of x we have, which is x to the s for this one. And then again, at the very end, we will have a general term. But instead of our general term being x to the n, now our general term is x to the n plus s. So now we fill in this table, the rows of this table, with the terms in our power series. And now we have the table we need, and we can actually begin to fill this out. So let's start with the red row first, the x squared y double prime. So I recommend when you fill out this table, for each term, think about what value of n do I need to get this power of x. So we look up at our x squared y double prime term, and we ask ourselves, to get a power of x to the s, what value of n do we need? And hopefully you can see that you would need a value of n equals 0. With a value of n equals 0, this means our coefficient is just s times s minus 1 times a sub 0. Then we follow the process for the rest of this row. N equals 1 will give us our x to the s plus 1 term, and that will leave us with a coefficient of s plus 1 times s times a1. To obtain the x to the s plus 2 power, we need n equals 2, which leaves us with a coefficient of s plus 2 times s plus 1 times a sub 2. And last but not least, our general term, to get a power of x to the n plus s, we need to plug in, well, n equals n. So we end up with a coefficient of n plus s times n plus s minus 1 times a sub n. And then we repeat this process for the remaining terms in our differential equation. I highly recommend that you pause the video right now and give this a go yourself and use my work to check your answer. So go do that. For the next term in our differential equation, 4x times y prime, to get an x to the s term, we need to plug in, again, n equals 0, which leaves us with a coefficient of 4s times a naught. For the x to the s plus 1 term, we need to plug in n equals 1, which leaves us with 4 times s plus 1 times a1. For the following term, we need n equals 2, leaving us a coefficient of 4 times s plus 2 times a sub 2. And last but not least, for the general term, we need to plug in n equals n, which leaves us 4 times s plus n times a sub n. I'm going to skip the green row for now, and we'll come back to that one, and let's just jump right down to the last row. This one's pretty straightforward. N equals 0 will give us our first term, which has a coefficient of 2a naught. N equals 1 gives us our second term, which has a coefficient of 2a1. N equals 2 gives us our third term, which has a coefficient of 2a2. And n equals n gives us our last term and gives us a coefficient of 2an. Now, on to the tricky one. what value of n will give us a power of x of s for this green series? So what value of n do we have to plug in for this to give us n or x to the s power? And the answer is -2. But n doesn't go down to -2, it starts at 0, so we don't have a term for this term for x to the s. Nor do we have one for x to the s plus 1. Because when we plug in n equals 0 to that green expression, we get a power of x to the s plus 2. And that coefficient then is just a0. Now, to get the x to the n plus s term, we look up here at our series for this term and say, well, if I replaced all of my n's with n minus 2's, then I would get what I want. I would get the power of x to the n plus s. So to find my coefficient, I do that. I replace all of my n's with n minus 2's. So a sub n becomes a sub n minus 2. And we now have everything we need in our table. And we are now ready to find the next step. So I'm actually going to do this next step over here. And the next step is to use the column for the lowest power of x to find something called the indicial equation, and use that to find the value or values of s. So this means we need to add up all of our powers that appear, or all of the coefficients that appear in that first column, and they all need to add up to 0. So this means that s times s minus 1 times a0 plus 4s times a0 plus 2a0 has to equal 0. And then we can rearrange this. We end up with quantity s squared plus 3s plus 2 times a0 equals 0. But recall at this point that we've already assumed that a0 is not equal to 0. So that means instead the rest of this term must be equal to 0. So s squared plus 3s plus 2 must be equal to 0. And s squared plus 3s plus 2 can be factored as s plus 2 times s plus 1. Which gives us values for s of -2 or -1. And we will end up using both of these values at the end of the day. So we've reached a major milestone here. We now know the values for s that are going to appear in our solutions, which means one of our solutions is going to start with an x to the -2 power, and the other solution is going to start with an x to the -1 power. So what I'm going to do now is I am going to clear off this page. Keep it handy because you'll need some of these numbers for our future work. And we're going to move on to the next step here. And the next step in the method of Frobenius is step 5. And in step 5, we find the solution to our differential equation for each value of s separately by using the table in a similar manner as we did to the regular series solutions of differential equations. So I'm going to start with the s equals -1 term and work through that solution. So by looking at the second column here, we can learn something about A1. So go back and look at those coefficients in your table, and remember each column, the coefficients have to add up to 0. The coefficients have to add up to 0. So for the second column in our table, we get the following expression. S plus 1 times s plus 4 times s plus 1 plus 2, that whole thing times a1 equals 0. Well, once we plug in values for s here, this gives us that 2 a1 equals 0. So we can say for sure that a1 definitely equals 0. a1 does not equal 0, but a1 does. Now, A lot of the time, after we consider the second column, we're just going to jump straight to the general term. So we are just going to jump right to the last column of this table, and we get the following expression by setting all of our coefficients added together equal to 0. N plus s times n plus s minus 1 times an plus 4 times s plus n times a sub n plus a sub n minus 2 plus 2a sub n equals 0. Now, plugging in our actual value for s here, this becomes the following. N minus 1 times n minus 2 an plus 4 times n minus 1 an plus a sub n minus 2 plus 2 times a sub n. And then we can rearrange this whole thing as follows. Which means we can now write our general relationship between our terms as follows over here, that any given coefficient is equal to negative of the coefficient that came 2 before it, divided by n times n plus 1. So now we have our general relationship between our coefficients, and we can actually go about the trouble of figuring out what our actual solution looks like here. So let's go through that. We know a1 equals 0. So when we try to think about a3, well, a3 will equal negative a1 divided by something. But since a3 depends on a1, a3 will also be equal to 0. And so will a5 and a7 and a9 and so on and so on. All of our odd numbered a's will be 0. But we still need to look at our even numbered a's. So let's do those kind of one at a time here. a2, based on our general relationship, should be negative a0 divided by our n and n plus 1. So n is 2, and n plus 1 is 3, so divided by 3 times 2. So we could write a2 as negative a0 divided by 3 factorial. a4, on the other hand, is negative a2 divided by 4 times 5, n times n plus 1. And we can plug in our value for a2 that we just found in this previous step to see that we get a0 over 5 factorial. Following the same pattern along for a6, we get negative a0 over 7 factorial, and so on. So since we have a good idea what's happening with our coefficients, we can now write out the full form of our solution here, or at least our solution for s minus 1, s equals minus 1. So I'm going to call this solution y sub 1, and we have a0 times x to the s as our first term, and s is minus 1. And then our next term will be the n equals 2 term, so we'll have a coefficient of negative a0 over 3 factorial times x to the 1 this time, because this is the n equals 2 term, and don't forget we have x to the n plus s, or x to the 2 minus 1 here. Writing out future terms, the next term ends up being a0 x cubed over 5 factorial. The following term is minus a0 x to the 5th over 7 factorial, and so on. And we can come up with a helpful way to rewrite this to make things look a little more familiar, because there's nothing wrong with this solution as it's written. But we have experience with common series solutions for various functions, so let's see if we can massage this to look like one of our standard series solutions. And one thing that's jumping out at me here is that our signs are alternating between the terms, plus, minus. And then we have a 1 over 3 factorial, a 1 over 5 factorial, a 1 over 7 factorial, and this seems an awful lot like the series for sine of x to me. So let's factor something out of this expression to make it look a little more like sine of x. I'm going to factor out an a0 times x to the negative 2 of every single term. And for our first term, that leaves us x. For our second term, that leaves us x cubed over 3 factorial. For our third term, we're left with x to the 5th over 5 factorial, then minus x to the 7th over 7 factorial, and so on. And would you look at that? This bit in the square brackets here really is the power series expansion for sine of x. So we're lucky enough here that we can actually write out our solution analytically as a naught times sine of x divided by x squared. There's the x to the negative 2 power. So we've now found a solution for s equals negative 1. And then we're going to have to find the solution for x equals negative 2 as well. So let me clear some space and we'll begin that process. Now we need to find the solution for s equals negative 2. I highly recommend pausing the video for this and trying this one out yourself, seeing if you can figure it out and how far you can get, and using this video to check your work. This is actually one of the homework problems in the textbook. It's not one I've assigned, but they do not actually do the s equals negative 2 example as part of this section, and I'm going to do it here for you so that we can go through an entire problem. So, starting from the same place we did before, we're going to look at the second column to see if we can learn something about A1 here. So the second column was just repeating what I had written before. S plus 1 times S plus 4 times S plus 1 plus 2 times A1 has to equal 0. Well, when we plug in our value for S here of negative 2, we end up with, in parentheses, 2 plus 4 times negative 1, plus 2 times A1 equals 0, or 0 equals 0 no matter what the value is for A1. So this means that A1 does not have to be 0, so we're going to have to assume that A1 is not equal to 0. And then just like before, we're going to jump straight to the last column. I'm not going to, or yes, I will. I will rewrite out the individual entries from the last column that are as follows. N plus s times n plus s minus 1 times a sub n plus 4 times n plus s times a sub n plus a sub n minus 2 plus 2 a sub n all equals 0. And then we need to plug in our value of s equals negative 2 into this expression and simplify it down to solve for our general relationship between the variables. So here's what that all looks like, kind of blurring through the math here. So at the end of the day, we get n squared minus n times a sub n equals negative a sub n minus 2, or writing this a little bit differently, and I'm going to bring this up here to save some space, we get our general relationship that a sub n is negative a sub n minus 2 over n times n minus 1. So a very similar relationship to before, but slightly different this time around. And now we're going to do exactly what we did before. We're going to figure out what all of our coefficients are in terms of any indeterminate coefficients we have. So, starting with a naught, well, a naught is a naught, so at least we have that one, that's nice. A2 is then going to be negative a naught divided by 2 times 1, or negative a naught divided by 2 factorial. Then a sub 4 is going to be negative a2 divided by 4 times 3, which, plugging in the expression from our previous line, we get a naught over 4 factorial, positive this time. Then for a6, it will turn out that we get negative a naught over 6 factorial, and so on. But now we also need to look at our a1 term and all the terms that depend on it. So a1 equals a1, but a3 is negative a1 over 3 times 2, which is equivalent to negative a1 over 3 factorial. Then a sub 5 is negative a3 over 5 times 4, which, after we plug in our expression from our previous line, gives us a1 over 5 times 4 times 3 times 2 times 1, which is 5 factorial. And then a7 will equal negative a1 over 7 factorial, and so on. So now we're actually ready to start writing out our solution here. I hope I have enough room, but we'll see. So I'm going to call this solution y2. And this solution is going to have a couple of sets of terms all at once in it. So let's start at the very beginning with a naught. So the constant term is a naught times x to the s, which is x to the negative 2. Then we'll have another indeterminate term, a1 times x to the s plus 1, which is to the negative 1. And then we can go on with future terms. Our n equals 2 term just ends up being a naught over 2 factorial. Then our next term is a1 times x over 3 factorial plus a naught x squared over 4 factorial plus a1 x to the third over 5 factorial minus and so on and so on. Sorry, I kind of overlapped myself there. Poor board management, my bad. So let's split these into even and odd powers of x. They seem to be doing different things, and it might be easier to express everything that way. So, writing this all out separately for even and odd powers. For the even powers, we have a naught times x to the negative 2 minus x to the 0, I'll write it out explicitly, over 2 factorial plus x squared over 4 factorial, and so on. And then for our a1 terms, we have x to the negative 1 minus x, well, just x, not x to any power, over 3 factorial, plus x cubed over 5 factorial, and so on. And now again, we want to look at this and see if we can massage this in some way to look like a power series we recognize. And the series for a naught has a term with no factorial on the bottom, then an over 2 factorial over 4 factorial, and the terms alternate positive and negative. This looks a lot like a cosine to me, a lot like the power series for cosine. And if I factor out an x to the negative 2 power of this expression, we'll see that that's precisely what we get. Because we're left with, inside the parentheses, 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, and so on. And then for a1, this again looks an awful lot like a sine. And if we factor out an x to the negative 2 power, it will turn out that that's exactly what's left inside of this parentheses here. X minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and so on. So we are almost done here. We can write our analytical solution for y2 as a naught times cosine of x over x squared plus a1 times sine of x over x squared. So we have now completed step 5. Finally, we have a solution that goes specifically with s equals negative 1 that we found on the previous slide, and now we have this solution, y2, which goes with s equals negative 2. Now we are finally ready for the last step in this process. I need to clear some space. There we go. So now step 6 is to state that the final answer, the final solution to our differential equation, is a linear combination of the two solutions we just found. So, I am going to write this linear combination in the following form. Y, the actual solution to our differential equation, is capital A times y1 plus capital B times y2. And let's plug our values or expressions for y1 and y2 into this to see if we can massage this down to a nicer form at all. So for y1, we have, well, big A times y1, which is a naught, sine of x divided by x squared. And then we have b times y2. So one of those terms gives us b times, I'm changing a naught here to b naught because there's no reason the a naught from the s equals -1 series has to be the same value as the a naught for the y2 series. So my a naughts and a1s and a_n's in the second series we found, second solution we found, I'm just going to call those b's instead. So capital B times b naught times cosine of x divided by x squared. And then the last part of y2, still the capital B out front, but this time times b1 sine of x over x squared. Well, we have some like terms here. We have two sine terms, so we can combine our sine terms together into capital A times a naught plus capital B times b1 sine of x all over x squared. Plus capital B times b naught times cosine of x over x squared, which gives us, combining those constants all into one, because capital A naught, capital B, and b1 are all just constants. So I'm just going to give that collective grouping of constants a new name and call it C. So that first term becomes C sine of x over x squared. And capital B times b naught I'm going to call D. So that's D cosine of x over x squared. So we end up with our final answer here of C sine of x plus D cosine of x, the whole thing over x squared. And this is the answer to our differential equation. We had, as a reminder, a second order differential equation, and our solution here has two arbitrary constants. So that means this is the general solution. No more looking is necessary, and the worst you'd have to do is figure out what specific values of C and D we need to match with our particular situation based on initial conditions. So, that is everything for the method of Frobenius. It is a long and cumbersome process, but it is a very step-by-step process where you know what you're supposed to be doing in each individual step, and there's just a lot of grinding through algebra. But this brute force approach will work for an awful lot of differential equations that we need to solve. The important bit here is that our normal method of obtaining series solutions to differential equations could not have solved this problem. There is no power series representation for something like this that has a 1 over x power, at least not something that converges everywhere. But now we have an analytical function that will describe the solution to this differential equation. Don't forget all about the things we have due this week. There's a lot of them. And thanks for watching, and have a good day.